Alright, welcome back to the second part of our network security course about the topic of computer networks and the internet. Last time we were talking about sockets, and actually we divided the internet protocol into layers called application layer, transport layer, network layer, link layer, and physical layer. So we talk about a little bit about transport layer, and we talk about sockets, and actually sockets was the part that helps us to connect processes with the transport layer. So we actually summarized it up like this. A socket is the interface between the application process and the transport layer protocol. So the sending application pushes messages through the socket. The transport layer protocol on the receiver side gets the message to the socket of the receiving process. So there are like 4 characteristics of transport services for applications. Some of them actually called data integrity, timing, throughput, and security. We already talked about data integrity actually because we spent more than a week on cryptographic hash functions, so we already know about this topic. Some applications, for example file transfer or web transactions, require 100% reliable data transfers. So you can provide this with data integrity. And some other applications like streaming audio or something can tolerate some loss. For the timing, some applications, for example internet telephony, interactive games, require low delay to be effective. And for the throughput, some applications like multimedia require minimum amount of throughput to be effective. And other applications, called elastic applications, they make use of whatever throughput they get. For instance, for file transfer, it depends on how fast the communication you have. If it's fast, you download it faster. If it's slow, then you wait a little bit more. For the security, we already actually covered this topic in this course. We talk about every cryptographic algorithm, the cryptographic solutions for encryption, like symmetric encryption and asymmetric encryption. We also talk about data integrity with the topic of cryptographic hash functions. We also talk about authenticated encryption. So the security is the part that we already covered. So we already know this part. Let's focus on the other topics. So let's look at some common apps, these applications and their characteristics. So file transfer cannot tolerate data loss. The throughput is elastic and it is not time sensitive. Email is the same. You need a reliable data transfer here. And for web documents, again, you require 100% reliable communication. You cannot tolerate any data loss. But for real-time audio and video, you can tolerate some loss. And for the throughput, audio should be at least 5 kilobits per second. Depending on the quality of the audio, the throughput can reach to 1 megabits per second. And for video, it depends on the resolution and how good you compress the video. But again, it's something between these values, the throughput. And these are also time sensitive, like 100 milliseconds or so. This is important because if the connection is not that good and the delay between communication exceeds this number, then it will be hard for people to communicate. And actually this happens from time to time when you are having a WhatsApp call, because if the one party has a bad communication at some point, then because of the delay, people will not be able to hear themselves and start talking at the same time and so on. So it is time sensitive. For the stored audio and video, again you can tolerate some data loss. Throughput is the same as above, and time sensitivity is a few seconds. So I think here we can also talk about a little bit more about how much data loss you can tolerate. So for instance, in my previous video, I recorded in a good quality, but then I compressed it using the algorithm like H264, which is for video compression. But for the audio compression, I used MP3 format with 128 kilobits per second. So normally this is a very good quality actually for a simple voice. But What happened next, I think the YouTube also compressed it when I uploaded the video. So this is why I don't like the sound quality of the previous video. So here we say we can tolerate data loss, but it is up to a point, because if the sound quality or video quality is really troubling you, then this means that you cannot watch an hour of video that you don't like the audio or the quality of the video. So you can tolerate it up to some point. For the interactive games, again, you can tolerate some data loss. Throughput is a few kilobits per second or up, and it is time sensitive. Yes, again, if it exceeds 100 milliseconds, then you won't be interact with other players in a good way, because the things you are seeing probably happened a few seconds ago, so this actually prevents you to play the game and so on. And for text messaging, you rely data. You cannot tolerate any data loss. The throughput is elastic, depends on how good your communication is. Time sensitive, yes and no. I mean, it doesn't matter if your SMS reaches in 1 second or 10 seconds, but if it goes in if it is delayed like 3 days, then yeah, it's time sensitive. So Internet Transport Protocol services, we actually use two services here, TCP and UDP. And TCP actually is the one that we use most of the time, because it provides reliable transport between sending and receiving process. There are no missing or duplicate bytes. It has flow control. Sender won't overwhelm receiver. And it has congestion control. It throttles sender when network overloaded. So actually this is what happens when you are actually watching a YouTube video. If you start watching it at for instance at full HD, but your internet connection is slow, then due to congestion control, YouTube can understand that it is overwhelming the receiver, so it throttles down by actually reducing the quality of the video, for instance going back down to 720p or maybe 360p. So this way you watch a kind of a bad video, but you still continue watching it. And when your internet connection goes back to normal, the YouTube understands it and gives you the full HD video back. It does not provide timing, minimum throughput guarantee, or security. These are the bad things about TCP. It is connection oriented. Setup required between client and server processes. Let's move on to UDP service. Unlike TCP, it is unreliable data transfer between sending and receiving process. So this is the bad thing about UDP. Good thing is that there is no handshaking before the two processes start to communicate, so you gain some time. Does not provide reliability, flow control, congestion control, timing, throughput guarantee, security, or connection setup. So as you can see, there are a lot of bad things about UDP here. So you might at this point think that why do we bother at all? If this is the case, why don't we use TCP all the time? Why is there UDP? Actually, UDP, you might, some applications you would prefer UDP when you don't need reliable data transfer. You would use UDP for performance. Okay, now let's talk about how do we secure TCP or UDP, because we know that TCP and UDP has no encryption. So clear text, unencrypted passwords sent into the circuit traverse the internet in clear text. So this is a problem, and actually this was like a normal thing in like 10 years ago, because a lot of web pages has services like forums and so on, where you get a username and password and use it to connect to this service, but they were using it with TCP directly, and anybody who listens to the communication could capture your passwords and then capture your account or impersonate you and so on. So in order to overcome this problem, SSL is introduced, which is Secure Sockets Layer. This is an enhancement for TCP implemented at the application layer. So it provides encrypted TCP connection, or TCP enhanced with SSL, It provides data integrity and endpoint authentication. So SSL is not a third internet transport protocol. It is just applications use SSL libraries which talk to TCP. So this way you get encryption. So SSL socket API actually allows you to, if you use it, then clear text password sent into socket traverse internet encrypted. So you are just actually using a library. So this SSL was the initial name when Netscape started this, but then the name became TLS, which is short for Transport Layer Security. So after SSL version 3.1, we started with TLS 1.0, and now we have, a few years ago, we had the TLS 1.3, but most browsers or servers support 1.1, 1.2 and 1.3, and a lot of people are still using older versions like 1.1. But it is always advisable to use the latest version, especially for the cryptographic algorithms that are used, because TLS 1.3 chooses better cryptographic algorithms than the previous ones. Especially you can force your browser to use TLS 1.3 or something, but this may end up in bad user experience, because some of the web pages may not support the TLS version that you are using. And some browsers still allow usage of TLS 1.0, but this is a very, very bad idea, because this means that you are using a very old cryptographic algorithms which can be broken. So it doesn't allow your browser to use very old versions of TLS. So let's look at some internet applications and look at the application layer protocol and underlying transport layer protocol. So at the email, we have the protocol called SMTP. You can look at the request for commands document at this number. Since we require reliable communication, we have to use the TCP. For remote terminal access, we have Telnet. Again, we need TCP here. For web, we use the HTTP protocol. It uses also TCP. For file transfer, we have file transfer protocol FTP. Again, it uses TCP. But for streaming multimedia, you can use HTTP like the web pages like YouTube uses, or you can have a different protocol like RTP. And here the underlying transport protocol can be TCP or UDP. It depends on you. For the speed, you might prefer UDP, and for reliability, you might end up with TCP. For internet telephony, same thing applies. You can either use TCP or UDP, and you have some protocols like SIP, RTP, or some proprietary algorithms like Skype uses their own algorithm. So let's look at the application layer protocols. An application layer protocol defines types of messages exchanged, like request and response. It defines message syntax, what fields in messages and how fields are defined. It defines message semantics, meaning of information in fields, rules for when and how processes send and respond to messages. These are the parts where application layer protocol defines. There are also open protocols and proprietary protocols. These are open protocols are defined in RFCs, and some companies use their own algorithms or protocols. So let's move on to web's application layer protocol, HTTP, which we use every day, and actually which you are using now because you are watching this video at YouTube. So World Wide Web was a public internet application, and initially the internet was actually kind of needed for universities to communicate with each other. So at this point there was no need for security, because you are actually trying to send some information. You didn't care if the information leaks. So this is why HTTP does not provide encryption itself. So this is actually a simple protocol. A web page consists of objects. An object may be an HTML file. There might be images like JPEG images, Java applets, audio files, and so on. A web page consists of base HTML file, which includes several referenced objects. Each object is addressable by a URL. For example, you have the host name, and then path of the document you are trying to obtain. In this case, the object is a GIF file. So, how the HTTP hypertext transfer protocol works. So, this is web's application layer protocol, and this is a client-server model. So, as a client from our browser, either using a computer or a mobile phone or a tablet, the client browser sends a request to the server. So client browser that request receives and displays web objects through its socket interfaces. So you are sending some request, server sends you a response, and this response is displayed by the browser we are using. And the server is just web server sends using HTTP protocol objects in response to requests through its socket interfaces. So we already told that HTTP uses TCP. The client initiates TCP connection, so it creates a socket to server, and for HTTP the default port is 80. The server accepts TCP connection from the client. Then HTTP messages, the application layer protocol messages, are exchanged between browser, HTTP client, and web server, which is the HTTP server. Then the TCP connection is closed. But note that since it is just open at the beginning and then closed just afterwards, HTTP is stateless. Server maintains no information about past client requests. This is because we need actually speed, and we need a protocol that shouldn't be complex, because if you design a protocol that maintains state, then it becomes really complex, because past history and state must be maintained. If server and client crashes, their views of state may be inconsistent, so they must be reconciled and so on. HTTP connections can be divided into two categories, non-persistent and persistent HTTP. In the non-persistent case, at most one object sends over TCP connection, then connection closes. Downloading multiple objects requires multiple connections, so this is the cons of the non-persistent HTTP connections. But for the persistent HTTP, multiple objects can be sent over single TCP connection between client and server. So let's look at non-persistent HTTP, and we will look at the persistent HTTP. So suppose that the user just enters this URL and wants to visit this page, and assume that this web page contains some text in an HTML file, and it has references to 10 JPEG images. So the page contains 10 images and some text. So HTTP client initiates TCP connection to HTTP server at this on port 80. So server waiting for HTTP communications accepts this connection and notifies the client. Now client sends the request message containing URL into TCP connection socket. Message indicates that client wants object this. So HTTP server receives this request and forms the response containing requested objects and send message into its socket. So at this point you have to actually, not directly related to this, but if the thing that we are going to send here is an HTML file, then actually it is a static data, so the server just sends it back. But if it is not an HTML, but it is a dynamic content like PHP or Perl or CGI, then the server performs an operation and forms the response message and then sends it back. So this is why visiting like old web pages or web pages that consist of only HTMLs are really fast compared to other web pages which uses databases and so on. So once you prepare the object, you send it back. HTTP server closes TCP connection because this is a non-persistent HTTP communication. Now what the client receives is that it receives the response message containing HTML file which contains the text and displays this HTML file, but in the HTML file there are 10 JPEG images that are referenced, so there are also 10 different objects which you haven't received at this point. So what you do is go back to step 1 and repeat it until this step for each 10 JPEG images. So you have to reconnect to the server. So you have to reinitiate the TCP connection 10 more times. So just for this web page, you have to do 11 TCP connections. So let's look at the response time and why moving on to persistent HTTP will reduce our response time. So we measured with RTT, round trip time. This is time for a small packet to travel from client to server and back. So when the client initiates a TCP connection, you send the initiation request. So server acknowledges it. So this is one RTT. Then you request for to download of an object, and server sends it back to you. But now it also takes one more RTT, but plus the amount of time required to send this file. If it is a small file, then you will receive it in a very fast way, but otherwise it will take some time. So non-persistent HTTP response time equals to these 2 RTTs plus file transmission time, which depends on the file size and connection speed and so on. But if, as I told you, this is a problem because it requires 2 RTTs per object, and moreover, for every object you are initiating a new TCP connection which might overhead the operating system. This is why we might prefer persistent HTTP, which is also known as HTTP keep alive. So server leaves connection open after sending response. Subsequent HTTP messages between same client server sent over open connection. Client sends request as soon as it encounters a referenced object, as little as 1 RTT for all the referenced objects, plus of course downloading the file time. So what kind of HTTP messages that we are sending? So there are 2 types of HTTP messages, request and response. HTTP request message is actually in ASCII format, which is a human readable format. So first line is the request line. It might start with get, post, head, put, and commands like delete. Generally, when you are requesting something for the first time, you have to use get. So in this case, you want to download the object index.html. So this is the version number, and then you have carries, return character, and line feed character. Then you have headers, and at the end of headers, you also put a carries, return, and line feed, so that this indicates the end of header lines. So general format of a HTTP request message is as follows. You put the method here, URL, version. This is your request line. Then you have headers and their values. And at the end you have the message body. So if you are using a get command, since you are requesting something, you don't have anything to send. So you don't have an entity body there. So as it is also mentioned, the entity body is empty with the get method because you are requesting something. But if you are using a post method, for instance, if you are filling a form online, then this means that you are also sending some data. Then at that point you have to use the post method, and then you can use the data you put it in the form to enter the body. The post method is also used for requesting a web page from the server. An HTTP client often uses post when the user fills out a form. Input is overloaded to server in entity body. But if you prefer to use a get method, then you can put your data at the URL. For instance, this is called URL method. This time instead of post you use the get method, but input is uploaded in URL field of request line like this. So this is the web page you want to visit, but after question mark you actually provide some values or parameters that you want to send. And here instead of the post method you are using get method, so you have to put your data here. If you prefer to use post method, then you can erase this part because you will sending this data here, not at the URL. So, and a typical HTTP response message looks like this. This is the status line, again the version, and now the status code is actually tells you what happened. 200 this means that it is okay. You have again header lines, then at the end, after the headers, you have the requested data, in this case an HTML file. So there are a lot of HTTP response status codes. You can actually find the full list on the internet, and these status codes appear in first line in server to client response messages. Some example codes are 200, which means okay. This means that request succeeded, requested object will appear later in this message. If you see 301, this means move permanently. This means the requested object moved. New location specified later in this message at the location header. So if your browser is clever enough, they can look at there and take you to the new location of the object that you wanted to visit. 400 is the code for bad request. This means the request message not understood by server. 404, maybe the most famous one, is not found. Requested document not found on the server. So actually you have to be careful about this error, because once you receive this error, maybe this doesn't mean that actually that object is no longer there. Maybe the server is currently maybe restarting its stuff or something, so maybe you get a 404 and 1 minute later you can actually revisit the same URL and obtain the object. Another thing to consider is that sometimes even if your browser tells you 404, saying that the object not found, maybe this is due to your internet service provider. Maybe you wanted to visit a web page, but your internet service provider didn't want you to, and they can give you 404 error. And you can easily check if this is the case by using proxy or VPN. So this is kind of a general error. You have to be careful about what it means. Another one is 505, HTTP version not supported. So at the client side, actually you can use Telnet to see how these messages are obtained and what they look like. So you can actually use your Telnet to your favorite web server just with this command and with the port number. And if you type something very simple like get this, and you will then will obtain the response from the HTTP server. And you can use Wireshark to look at the captured HTTP request and response. But of course, Telnet can be used for educational purposes, let's say, but for security, in the past it has a lot of issues, so you shouldn't be using Telnet for other purposes than educational ones. Try to stay away from Telnet. Okay, so user server state cookies. So how we can keep this state, because most of the time we want to keep the state to get a better user experience. HTTP is a stateless protocol designed this way because of performance. An HTTP server does not keep track of the user request by HTTP. Websites use cookies for user identification. In other words, they are keeping the state of the user. And cookies are defined in RFC 6265. So how these cookies actually work? They have four components. A cookie header line in the HTTP response message, a cookie header line in the next HTTP request message, a cookie file kept on user's host, managed by user's browser, a backend database at the web page. So let's look at an example. Susan always accesses internet from her PC. She visits a specific e-commerce site for the first time. When initial HTTP request arrives at site, the site creates a unique ID and entry in the backend database for ID. So this is how it works. Let's say that this client has already visited eBay in the past, so in their computer they have a cookie file with the unique ID there, but they don't have a cookie file for Amazon because they haven't visited it yet. So when for the first time when they visited the web page, Amazon server, let's say, they send the usual HTTP request message. So Amazon receives this message and realizes that there is no cookie header here. So server creates a unique ID for this visitor, and in their response of the web page, they also say that set cookie to this. So the browser now creates a new cookie file for Amazon, and also Amazon creates an entry in their database with this unique ID for this user. Then this user goes to the web page, and Amazon prints their HTML file or whatever in there as their home page. 1 week later, if the same person wants to visit Amazon again, now in their request they also send the cookie, because browser notices that they already have a cookie in their computer. So they send it to Amazon. Now Amazon looks at the cookie and checks who this user is from their database. And depending on their previous actions, now Amazon can take a specific action. Let's say that can show you a web page where the items on the main page are something that you actually searched 1 week ago. So this is how commerce sites actually use cookies. They can use it for shopping charts and so on. So here is the similar picture. So cookies. Let's summarize them. Cookies can be used to identify a user. What cookies can be used for? Authorization, shopping carts, recommendations, user session state, like web email. How to keep state? So at the protocol endpoints, maintain state that sender receiver over multiple transactions, but cookies, you send them with HTTP messages, so this way you carry the state. But so they look really good, but in terms of privacy and security, there are some problems with cookies, because cookies permit sites to learn a lot about you. You may supply name and email to sites, but the problem is that until a few years ago, web pages really abused cookies. So they collected a lot of data about a lot of people, but after GDPR, people realized that this is illegal. But what happened next is that now every web page we visit says that this web page are using cookies, so you have to click OK to use the web page anyway. So they just inform you that they are collecting data about you, but your privacy is still lost. And from your browser you can say that okay, disable all of the cookies. You can do that, but now your user experience will be bad, because every time you visit a web page it doesn't remember anything. There's no state, so you lose usability. But what the browser should actually allow you to do is, actually you should be able to choose like 5 or 6 web pages about, like if you are using social media or something, just enable cookies at web pages like Facebook or YouTube or something, but disable all of the cookies on remaining web pages. So this would what I would prefer to be the default choice for a default setting for a browser. Okay, so now let's move on to one of the final topics, which is, first one is web caches. So far we have seen how the client and server interacts, but remember that at the beginning of this topic we mentioned the queuing delay. So if the clients are requesting a lot of data from the server, then there might be a queuing delay, and proxy servers might prevent this. So how does it work is as follows. A proxy server satisfies client requests without involving the origin server. So as a client, you send the request to your proxy server. Normally you are trying to get some object from this origin server, but once you send this request to proxy server requires that they already have the object that you want. So instead of communicating with the origin server, they just send you the object. But if they don't have the object, they will go to the origin server, obtain it, and then give it to you. So users can set a browser for web access via proxy server. The browser sends all HTTP requests to proxy server. So if the object is in cache, the cache returns object. Else, cache requests the object from the origin server, then returns the object to the client. Cache acts as both client and server. So it looks like a server for the original requesting client, but it looks like a client to the original server. Typically, cache is installed by internet service providers, by your university company or other ISP. But why do we use web caching? We are using it to reduce response time for client requests, and we use it to reduce traffic on an institution's access link to the internet. And internet is dense with caches. This enables poor content providers to effectively deliver content. So too does peer-to-peer file sharing. So let's give an example and why we may need a web cache. So let's look at this example. Suppose that the institutional network is connected to the internet by a 15 megabit per second link here. So you have a local area network, and here is the public internet, and your outward connection is, the capacity is 15 megabits per second. Let's say that here you have your local area network, and the clients are requesting objects with the average size of 1 megabits. The average request rate from client browsers to origin servers is 15 requests per second. So your institution actually receiving 15 requests per second. All of the requests have the size of 1 megabits in average. So you have to go to origin servers for this request and receive them back. And assume that server to client HTTP response is 2 seconds. So the data from internet actually takes 2 seconds for you to obtain. So what is the total response time from client to origin server and obtain it back? So initially what you have a local area network delay, so the time from here to here and after from here to here, but also the internet delay, so which is your institution request for the data from the origin server, and it receives it. So the sum of these both delays, so delay here and here, actually is your total response time. But the problem is that your local area network is fast, but your access link has a slower connection to the internet. So let's measure what happens. In the local area network, what happens is as follows. You are having 15 requests per second. All of the requests are in average 1 megabits. So you multiply them, but your local area network has 100 megabytes per second internet connection. So if you divide it, the result is 0.50. So this is actually a number between 0 and, actually it can exceed 1, but remember the queuing delay. We said that if it is close to 0, then there is no queuing delay, but if it is close to 1, then the queuing delay goes to infinity. So in this case it is very close to 0, so we say that this is this results in a negligible delay. So in this case let's say that this is just 10 milliseconds, which is negligible. But let's see what happens here. You are having 15 requests per second, which are 1 megabits per second in size, but the connection speed is 15 megabits per second. So when you divide it, it is 1. And again, remember from the slides, when this number approaches the 1, the delay on the link becomes large. Actually it goes to infinity. So this means that there is a huge delay here. What is the solution? Of course you can pay more money and increase this 15 megabit per second access link to something more, but it will cost you. But alternative solution is to use a web cache, which happens like this. So you put your institutional cache here. So it depends on how much actually you cache here, but the typical hit rate of a proxy server is about 0.2 to 0.7. This is the fraction of requests satisfied by the cache. So assume that the hit rate of the cache is 0.4 in our example. This means that whenever a client requests something, your institution realizes that 4 out of 10 times it is at the cache, and 6 out of 10 times it is at the origin server, which is not cached here. So let's assume these are the numbers in our example. So traffic intensity in this case reduces to 0.6, because in the previous slide, remember that it was 1 here. But now since only 60% of the data is sent to origin servers, now our traffic intensity reduces to 0.6. Assume that the local area delay is about 10 milliseconds and the internet delay is about 2 seconds for 0.8 traffic intensity. Total response time, in our case, this 0.8 actually should be 0.6. So total response time is 0.4 times this many seconds plus 0.6 times 2 seconds. So this is your total response time actually. So our final slide is for conditional get. So the goal is to don't send the object if cache has up-to-date cache version. So your institutional cache can use this, but also your browser might do the same trick. So idea is as follows: when the client requests something from the server, but the client has already visited the same web page previously and obtained the object, but it was like a few days ago. So here's the date of the time you received that object. So you are sending a request but saying that if modified since this date. So because you have the object at that date. So server looks at the date and realizes that that object not modified before it. So it sends you a HTTP response with 304, which means not modified. So we use this to so that we have no object transmission delay and lower link utilization. And cache is specified in the cache. We specify date of the cache copy in HTTP request like this, and server response contains no object if cache copy is up to date. So for this kind of reason, if you are, for instance, visiting a web page and refresh it in a millisecond, or sometimes what happens is as follows: if you are designing a web page, you update the web page and use your browser to see the new version, but your browser actually shows you the old one. This means that your client browser or the server didn't obtain the correct if modified since then. So if you refresh the web page, then you will obtain the new object or the new web page. Okay, so this will be all for our topic of computer networks and the internet, and we will see if the sound quality of this video will be better than the previous one.